because your heads are up. And start off on a Wednesday morning with a sensor talk that I'm really not that familiar with, but Wade was generous enough to send us his slides. Stuff we didn't understand, we replaced with stuff we knew from our own stuff, our own data, our own slides. Jared's going to help me in on the aerial imagery part of things and the camera part of things. So if there's something here you fundamentally disagree with or you don't like, those are Wade's slides. The ones that are really good are ones Jared and I did. So send all your criticisms to Wade. But we're going to talk a little bit about sensors. There's a wide array of them, and there's a lot of marketing that is done to say why you need all these sensors in all your fields all the time or you're a bad farmer. So we're going to try and wade through what all these things do, how they work, when you can use them, when it's appropriate and when it's not, and then try and discuss a little bit about whether there's an ROI there, but that's going to be a kind of vague discussion. So Wade laid things out as two main fields as far as two technology approaches. One is an information-intensive approach that looks at field-level data to make decisions. So stuff that you're pulling out of the field that you're going to use to make a decision either this year, in season, or for next year. And the problem, one of the problems with that is it requires a lot of additional data to be generated. You're not going right into it and saying, here's the answer before we ever start, or here's the information we need before we start. We've got to generate that information before we can start making those decisions. And IPM will be an example of that. We've got to start looking at what our thresholds are before we can start making decisions. Or we got the embodied knowledge, and that's basically the stuff that you're buying, the technology that's coming in the bag. You don't really have to add any skill to grow Roundup Ready beans. You just buy the Roundup Ready trait. So there's two different sides, the embodied knowledge versus the information intensive. So when we look at the information intensive side, you've got things like yield monitors that's going to show you here, this area of the field is going to do worse than that area. Maybe you ought to start looking at VRT. And that leads into a really heavy data-driven decision-making process versus the embodied knowledge, which is your stuff like automated guidance, your auto steer, your variable rate, sensors that are adjusting your variable rate on the go, those kind of things. So basically, to summarize, on the left is the hard stuff, on the right is the easy stuff. Today we're going to be talking about the stuff on the left. Okay. So soil sensors. Everybody knows that there's capabilities out there now to do a very good job of mapping soils beyond the old soil survey books that we used to have or what's on Web Soil Survey. That has value. The Web Soil Survey has got great information on it, but we can go a little farther. We can get a little more in detailed stuff. And then we can apply that for management. So one of those things that's going to be an example today is a project from Clemson. It's a specific nematicide placement project. They're running over their acres with a Varus. That's the Varus machine. It's not anything particularly new. They've been around 20 years or better. Going across fields and trying to delineate differences between parts of the field versus others. And they generated this map to define their management zones using that Varus. And there's some legwork involved. You know, the Varus machine will tell you that part of the field is different than another part of the field, and you can start grouping them and making this map. But you still don't know the little piece of information, in this case, of what your nematode density is. So you've delineated the zones using the Varus. You've decided more than likely this is the highest sandiest part of the field. You go back and sample and say, gee whiz, we've got more nematodes there in the high sandy part. Who would have thought? So maybe we need to look at this being a zone for a nematicide application where some of these other mid to low ranges are something different. So here at Clemson, they went back and started making georeferenced nematicide applications on a variable rate level, changing their rate of temic in this case across the field based on soil type. That data coming from the Varus survey that was done pre-season. So that is one thing, one example of stuff that can be done using that sensor technology. One of the other ones, well, they also applied it using planters as opposed to doing a broadcast or a sprayer application. This takes a lot of technology because you have not only to have the ability to sample the field, to make the map, the knowledge to make that delineated map, then to determine what rate should go where, but then you also have the ability to apply it on a variable rate basis, which is not necessarily everybody doesn't have that by default. Other uses for that EC map, this is University of Delaware's Warrington Farm when we do all our irrigation research. This is a deep EC map with our plots laid over the top of it, and I use that map to help me determine that if we're looking at a project that's got 10 treatments, I don't want all 10 of, or excuse me, all 5 replications of treatment 1 to end up in this red area. I want to make sure that treatment 1 ends up in red, treatment or replication 2 ends up in an orange, rep 3 ends up in a yellow and a green. And that's something that can be used when you're starting to do variety trials. We start to do strip trials in your field to look at different materials, different products. You want to make sure they don't all end up in one specific soil type. And the thing that caught us off guard this year is I'd always been using our shallow EC value to help do that determination. If you'll notice on the chart over here, we're looking at DPC. That's a Varus reading that is showing the electrical conductivity from 0 to 3 feet. So the deeper value rather than the shallow that's just 0 to 12 inches. We saw patterns in our drone imagery that had this little arc in soybeans this year and didn't really know why. And went back and looked at the DPC, and matter of fact, there's sand down to 3 feet. And that's why the beans didn't really look so good there. So with all the information that we had, we made a mistake. We put some plots where we shouldn't have put them had we been looking at DPC instead of shallow. So there's a lot of more information than sometimes we can even process here. So that map was generated with this MPS-3 Varus machine. It's about 6 years old. It came from Willard, thus the Willard stickers. They decided that it was sitting in their shed for quite some time, that University of Delaware would maybe get a little more value out of it. And this machine gives us the ability to not only do electrical conductivity mapping, but it has an organic matter sensor that's located in here, and it has a pH meter. And that pH sampler, depending on how fast we're driving and how close our passes are, getting anywhere from 60 to 160 pH samples per acre. It's really dense pH map, and nothing we're going to do with a grid sample by any means. However, as good as that sounds, it's only as good as the operator that's running the Varus. So my first glance was to say, wow, we've really got some areas where the line truck missed on these red streaks going across this field. Yeah, we've got to hire a different line truck operator here. But on further examination, the soil wasn't washing all the way off the sensor, and the operator wasn't catching it. So this reading on this end was the same for the whole pass all the way down until he got around and hit the bump on the end and the dirt fell off the sensor. And then he'd come back and get good data. So you could go wrong with these things, and that's what I think Wade was meaning by the good and the bad. It's a good tool as long as you're using it appropriately, but don't let it steer you in the wrong direction. So what's going to happen this year, this map is going to get redone with a little more attention paid to the pH sensor in particular, maybe an addition of a camera to make sure it is getting cleaned off between samples. But it does have value for us going forward. Now, I said that was a 6-year-old tool. There's newer tools out on the market. This is the same one by Varus called an iScan that is a much narrower tool that is meant to go in between planter units like you see here, mounted on a turbo till, a number of things, and everything's done in a line versus width-wise. So your EC is coming front to back and rather than side to side. They've incorporated a temperature sensor in there with the thought that if you're turbo tilling the head of the planter, you can get some idea of what the soil temperature is at a specific depth to say maybe part of this field isn't warmed up enough to really go in here and plant corn yet. I will put a word of caution on the organic matter piece of this. How many folks do their soil tests and get their organic matter readings from 0 to 2 inches? So this sensor, because it's not getting what you traditionally have with a soil probe, is likely in a no-till scenario going to show you an inflated organic matter value. If you're using that to drive an algorithm for variable rate seeding or fertilizer, it might send you the wrong way. Moisture, that can vary a lot within a field. And the original design behind this was to say, hey, we're going to look at how the moisture variability may affect whether we're ready to plant or not, and maybe we're not ready to go in particularly yet. So this leads into, because this unit isn't cheap, you're looking at $16,000 to add this onto a machine. So about 3 years ago, how many folks have ever heard of the smart firmer? Just a few. Okay, Precision Planting has got what's called the smart firmer. It replaces your Keaton seed firmer or whatever seed firmer you're using, and it's got a lot of the similar technology to what the Varus has in a much more compact unit. These things are about $500 a piece as opposed to $16,000. So it's something that people can really get perked up about. They had a few problems with the early designs as far as durability, but I think they've worked some of the kinks of that out. And the big feature that growers are using behind this is the ability to know whether they've got a clean seed trench. So how's that important? Well, if the seed trench isn't clean, you need to make some adjustments to your row cleaners. And if you've got clean sweeps or another product that's going to allow you to lift and adjust those row cleaners on the go, there's a potential that, yeah, maybe we need to put them down on one end of the field and raise them up on the other end of the field. There's some combination that needs to be happening there. Some folks have complained that in certain soil types, they will build up with clay. They start to get fatter, and you start to get bad readings. It's something that may work in Sussex County on sand, may not work on a silty clay loam. There's going to be some variations within that. Again, growers are seeing inflated organic matter values as opposed to what they're getting with a soil sample. But the moisture values, I see having definite benefits when it starts coming to soybeans. It's particularly dryland soybeans, so you can look at, all right, if we're planting at 1 inch, are we really getting into the moisture? Maybe we need to drop this machine down a little bit. And because that's right in the seed trench, you're getting a measurement of what's actually going on, where the seed's being placed. Folks have looked at temperature and haven't really found a correlation between the temperature and final yield, but it does give some folks some peace of mind as to whether, and maybe we may shut down and wait a couple days for the ground to warm up. But temperature seems to be more affected by this, in the smart farmer situation, by the ambient air temperature. That shallow soil really has a variability throughout the day as far as warming up versus deeper soil temperatures. Anybody have experience using these? Okay. I don't have any first-hand experience, but I have been around them, not when they're being used. With the precision planting monitors, this data can go back into display and change your seeding rate on the go based on what that sensor is telling you. So this is a direct reading and a direct response. So there's not a human interface that's making the decision to bump up, in this case, say, population because we saw an increase in organic matter. That machine does it on its own. All right, the other piece we can use from a Varus or a smart farmer is to combine that RTK elevation that most folks are getting out of an auto steer tractor nowadays and that EC value to start to do drainage and irrigation. So this is a field that has got some drainage issues, some serious drainage issues. And looking at this map, to me, the obvious way to drain this, the lowest spot of the field is down here. Maybe we dig a ditch across here or some swales, and we get the water out that way. The only problem is the only outlet is on this side of the farm. There's no way to go out with water that way. So this helped lead into a design like you see on the right, where all the water was being drained to a lift station, and it's being lifted up about 5 feet to get it out onto this side of the farm. That elevation and electrical conductivity data was what enabled us to draw this map to determine, hey, we do have enough grade, so this is what's coming out of the display, to say here's the slope, here's the proposed grade for a tile installation. We can adjust, hey, maybe it's going to happen, maybe it's not going to happen, maybe this particular pass, there is just too big of a hill for us to be able to pull through, and then come back and follow up with a tile machine. As you can tell, if you've never been around tile machines, it takes quite a bit of power to get this down in the ground. It is an ag engineer's dream to see that much fuel being burned at any given time. But in this scenario, we're able to get drain tile down. In this particular run, I think we're running at about 52 inches deep because it's going through a hill. And you can see the tractor's pawing pretty hard to get that down. We would not have been able to know whether that was even possible without having that data from the Varus and that elevation data coming out of the tractor beforehand. Because, well, I'm going to back up a step. I wouldn't have been able to figure out whether it was possible. NRCS does it on a regular basis by doing some manual surveys with a long length of time to do the engineering calculations as to whether the grade is there. This is something that was able to be done in an afternoon because we had that RTK grade GPS data coming out of the tractor. So going back to the electrical conductivity, this is just a demonstration on the differences between that 0 to 3 foot and 0 to 12 inch measurement. And in this case, there was a lot of clay and heavier soil down deep versus sandy soil on top. Just something to consider. And that data feeds back into if you ever want to do variable rate irrigation. Take a map like that. There's services that provide the information to do the map generation that says, hey, we're doing a good job of irrigating on 74% of this field. We have a rail variability of 26. If we did a sector control, speeding the machine up and down, we can get that to 21. That would not be optimally irrigated. And if we went ahead and spent the money and borrowed a variable rate irrigation system with adjustable nozzles that go on the fly, we can do 7% of that that's not optimally irrigated. And that all comes from that electrical conductivity data. Valmont and the University of Nebraska were showing a reduction in water, a reduction in nitrogen by trying to even that field out in response to soils. So changing gears a little bit, because we're irrigating, we need to know whether the water's going where we think it is, in the amount we think it is. Do we need to irrigate today, tomorrow, or the next day? And that's when soil moisture sensing comes into play. Soil moisture sensing is not anything new. It was done back in the 20s using tensiometers. We got into electronic capacitive sensors like this into the 90s. This probe is still being used today. I used them 20 years ago. They haven't really evolved a whole lot. What has changed is the in-field communications, and that is huge. So there's a number of different sensors that you can use, ranging from TDR to FDR, TDT, and we don't really need to get into how they work. But the key is most all these have features that allow that data to be relayed in-field between the sensors to a central point, to a cell phone, to a web application, and more importantly and more recently, to an advisor that is in a state 5 states away that is looking at what's going on in your field and giving you a phone call and saying, hey, John, you're getting ready to mess up big here. You better turn this pivot on. And that's some assurance that folks don't get, because when you get busy, you're not always going to stop and take the time to look at this data to see whether you're doing a good job. So those services have value, but I will put caution on there. In most of the cases, because of the cost of that probe that I showed you at the beginning, mostly this probe here, you're looking at $2,000 for one probe. And you put that in the field, and they're going to tell you, we'll put one of these in the field, and I can tell you what the 5 pivots around it, how you need to irrigate them. No. Because you guys know the variability within your fields. Where do you put that? Do you put it on the sandy land? Do you put it on the heavy land? Do you put it in the middle? My answer is you put it in all 3. You need 3 of them, minimum. Really, I like 4. I want 2 on my most predominant soil type because one of them is not going to work. So I want a backup plan. And then when that one, even if they are both working, one sensor says, hey, we're really, really, really dry. I'm like, I don't know if I believe that or not. I can look at sensor 2 and says, yeah, it says we're really, really, really dry. It gives you that second opinion to say we're right. Don't fall into the trap of trying to manage multiple pivots off of one sensor, because that could really go the wrong way. For anybody who was in the talk yesterday afternoon, it was a great talk on fertigation. The guys were geniuses that presented it. You saw the variability of how an irrigation system puts water out. What happens when you put that probe under that part of that irrigation system that's putting out 30% more water than the rest of the field? You've just driven all your farm to be irrigated off of something that's being artificially overwatered. This could send you the wrong way. So concentration is going to be the big thing. And the reason they only tell you one is because it's cost prohibitive to do more than one. There's other technology that feed back into this loop. This is infrared canopy temperature measurements. They're mounting them on center pivots now. They're putting them on platforms that go off the field. I think Jared's going to talk about some of the ability to do this potentially with drone technology. And then feed all that back into some multi-layered, multi-level, multi-method irrigation scheduling programs. We can take data, have been able for years, from a weather station using solar radiation, temperature, wind speed, and humidity, and estimate the evapotranspiration for any crop pretty stinking close. And I've run this against sensors for probably 15 years, and we're within 5% most years of being right on the money on the day as far as how that works. In an ideal format, hey, we run this scheduler, get a predicted value, and then feed that soil moisture back in there to say, yeah, you're right, or you're wrong. Maybe you need to make that adjustment. One of the advantages of using weather station technology to predict what you're using is you can kind of anticipate where you're going to be tomorrow rather than react to what happened yesterday. That's the problem with sensor stuff, is you're always trying to play catch up rather than look ahead. I really like the ability to be able to say, I don't really want to come in on 4th of July weekend to turn this pivot on with beach traffic. Can I run 5/10 instead of 4/10 on Friday and make it to Monday? And sometimes the answer is yes, sometimes the answer is no. This gives you that ability. Plus, the new versions build in weather forecasting that says we think we're going to use this much water tomorrow and the next day, and can kind of get more than yesterday we used 1/4 of an inch, but tomorrow we might be a little bit higher because it's supposed to be lower humidity or more sunshine or something along those lines. Some of these products are free. Some of them have a monthly charge. Some of them have a per acre charge. And they're available from all kinds of different sources. This is I believe that's out of Washington State. This is one provided by one of the irrigation dealers. Feeds right back into your phone, so you can make that decision when you're standing there in front of the pivot panel, decide whether you're going to turn this thing on. And with that, we're getting ready to get out of my expertise in wheelhouse. And I'm going to switch to the one that's knowledgeable regarding sensor technology from an airborne type thing rather than the in-ground stuff. Any questions on what we talked about so far? I'm glad you brought that up. I think the pH, what we've seen is versus soil testing with the pH, we'll take a sample with that machine after we've calibrated it and then take a soil sample right beside it. We're within a 0.5 point on pH. We're not as concerned about the absolute value because we're always going to do that soil sample to give us a correction value. I want to know the relative difference. So that's about the only way to generate that really dense map for the relative difference on the pH. Organic matter, I'm really glad you brought that up because I forgot to say it. Coastal plain soils, these organic matter sensors are not calibrated for us. They're calibrated for the Midwest. Is it likely that they'll ever be calibrated for us? Probably not. We're not the market for that stuff. Piedmont, they tend to work. Okay. I haven't tested them personally, but that's coming from other people's experience. But yes, a lot of this information, especially even the soil moisture sensors, they work well in a southwest climate, because that's where they're used, where they get 9 inches of rain a year and they really need to know exactly where they are to know exactly how much to put down. We are manipulating these sensors beyond their original design intention to make them work in our scenario.
Oops, not too far. The problem with the organic matter sensors and anything, it's only as good as the lab data it's correlated with. So if the lab data isn't very accurate, and if you've looked at organic matter data from a lab, it can be very variable itself. And that's my problem with some of these sensors. Like if the lab information that goes into calibrating the sensor isn't good, then the sensor itself isn't very good. But it's what you would want to get out of it. Is the organic matter enough between fields across an area to give you an idea? But if you want to know foot by foot that organic matter content, I'd probably never trust it out of a sensor.
I can't hear you.
Oh, yeah. All right, so we're going to talk a little bit about aerial remote sensing using sensors from planes and drones and satellites. So in-field, some of this can be done in-field, some of it's done remotely. How far away they define as remote, I don't know. Like your cell phone taking a picture could be remote sensing, I guess, to some people. But some of this has been around for a while, aerial photography, satellite imagery. Some things you can do in field, like chlorophyll meters, if anyone's ever used one of those where you go directly up to the leaf to measure the chlorophyll content. So there's some things that can be done up close by hand. There's some things that can be done from a distance. And what we're trying to do is figure out, can we do some of these things quickly and easier with less labor using remote sensing versus some of the field monitoring we've done. So I'll start off with Lidar because it has a lot less to do with plants and more to do with landscapes and soils. Lidar is light detection and ranging. If you know radar, that's radio detection and ranging. So Lidar uses lasers or light waves. Radio uses radio waves to detect and get reflection. So we've been using some of this probably since the 90s with planes to fly over top of the surface and then end up measuring the elevation. So this is actually Somerset County, Maryland, and you can see this escarpment right here where the elevation drops off. So the nice thing about Lidar compared to the elevation maps we had before, which were done with stereoscopy, they were done by hand in most cases, is they can be a lot more accurate in predicting elevation changes. And from these, you can develop slope and aspect maps. So if you are from Maryland, Maryland has a great GIS website that has every single county up there. They have a state map and they have per county maps, and you can actually go across and look at fields and see where there might be some elevation differences. And this is going to be a lot more accurate than any kind of elevation map you have. Outside of what James has with RTK on a tractor, this is the next best thing that we have in some of these states. 10 years ago, it was hard to get some of this data, but it's a lot easier to find state by state. So Lidar is not going to really detect plant heights. It typically goes through vegetation. But what it's going to be good for is detecting heights in the field. So like with what James said, it would be another source possibly for doing tile and surface drainage if you don't have RTK. So you can see this field here. This is actually a slope map. And this is one of Wade's slides. So you can see where the water is going at the edge, the darker area, that's the steeper slope. So you can take that elevation data and you can calculate slope aspect or just look at the elevations. You can see the ditches going across here. You can see possibly where wet spots are and then decide where you're going to put your tile drainage. We can use it as a topographic layer for precision ag. So if you're trying to match that up with a soil layer and create zones for fertility or variable rate application, you could use Lidar for that. And anything else outside of ag like road construction or community development. But a lot of the sensors that we're interested in ag aren't just for soils. We want to measure plants in the field. We want to measure, particularly in research, something like phenotyping for measuring plant characteristics. So right now, a lot of what we can do is do manual measurements of heights. If you've ever done tiller counts in wheat, which we're doing right now, and trying to match up with drones, it's very intensive, which is why most people don't do it. But we need those tiller counts in wheat to decide if we're going to add more nitrogen. So can we make that faster with remote sensing? So we have a lot more automated measurement than we can put out now. UD up on campus, and James helped put this together, has on an irrigation rig, they have a sensor that goes back and forth across that has Lidar on it to try to measure plant heights. And they're trying to see if we can use sensors to quickly assess plant characteristics in our research projects, which helps us a lot, but also maybe down the road they can help assess characteristics in fields to help farmers make decisions. So there's different equipment, and I have never used this. This is one of Wade's slides, but you can see this in-field phenotyping. So instead of measuring by hand, you can drive this equipment across there that takes these measurements for you and it inputs it into a data set. And it gives us more accurate numbers to look at our research and make decisions about what happened. Because even for us within research, it's hard to get labor to do some of this kind of work, to get very accurate data to tell you what actually happened. Sometimes when we have no conclusions, if we have information like this, we can get a better idea of what went on. So the name for this, and you're going to see it a lot more, it's going to be in a lot more research papers and what's going on, is high throughput phenotyping. This is on the left, you see the drone there, goes out in the field and takes pictures. All these different pictures are stitched together into an image that creates this NDVI, which I'll talk about in a minute. And from that, now, instead of trying to find enough students to walk out and take all these measurements for us in a plot, or spending an entire day going across that field, if you have the expertise and knowledge, you can extract all of that data within a few seconds with ArcGIS. It still takes some knowledge. We're still figuring out how to draw the plot maps over top of that, but we can quickly assess. We still, right now, have to do a lot of field measurements. That correlation I talked about with organic matter, I'm doing this with wheat. I still have to do the tiller counts to match it up to the NDVI data so I can create the equation that says whether or not we can do this down the road. But the great thing about this is maybe we can have this kind of information where people in consulting agencies or the government can fly across and take some quick measurements and get an idea of what's going on. So for remote sensing, we'll start off with satellite imagery. I talked about this a little last year in the remote sensing seminar that we had. When you talk about satellite data, and we are getting satellite imagery through, some farmers can get it through companies like Climate Field View. But you have to think about spatial and temporal resolution. Because there is free data out there. Landsat imagery is free. NAIP data is free. But what can you use it for? And the first thing you got to think about is the spatial resolution, which means how much does one pixel in that image represent? So for something like Google Earth versus Google Earth is going to pay high dollar for good satellite imagery, and you can zoom in and see something very well. Versus the free stuff right down there on the left, that satellite that says 15 to 30 meters, that's probably Landsat, and it's not going to help you set up any kind of zones in a field. versus something that you pay for. Temporal is how often do you get it. So if you were receiving imagery this summer from some of these companies, if the cloud cover went over, you might not have gotten an image for a month. And is that good enough to scout those crops or not? It all depends on what you're looking for. So you have to think about spatial and temporal resolution of satellite imagery. But satellites are originally where we got NDVI from, and there are a whole lot of different indexes that we talk about. So NDVI is Normalized Difference Vegetation Index. So when Landsat went up in the 70s, scientists looked at all the different bands that they were getting off of here. So this is a drone camera, but it'd be very similar to a satellite camera that they have up there. They have filters on these lenses that help us separate out these different bands of light: green, red, near infrared. And he did a bunch of calculations from the bands, and he figured out, because of the way near infrared is reflected off of the cellulose in plants, versus, we see green from a plant because it's reflected at us, but it absorbs red. He looked at these different ratios and figured out that we could use near infrared minus red divided by, and this is why we call it normalizing, near infrared plus red, and you can pretty much measure biomass. People say you're measuring plant health, but you're measuring biomass. So if you only plant one plant in a field, it's only going to show one plant. So if you have a plant that's sick and is dying, if there's less biomass, it should show up that way. So it's not necessarily a plant health index, it's more of a biomass index. But the nice thing about it is this original work with NDVI has given rise to some of the sensors that we're using now, and that's some of the sensors that we can use on drones. So that gets us to what we call an active versus a passive sensor. A satellite or your cell phone or a camera on a drone is a passive sensor. It's not creating its own signal, it's receiving a signal. The sunlight creates the wavelengths that reflect off the plants, and those sensors that receive them are passive. So that's a lot of what we use. Green Seeker, a lot of the crop sensors, those are active sensors. They create their own signal and bounce it off the plant. So something like Green Seeker puts out near-infrared and red light and receives it back and does the calculation. It doesn't have to count on the sun. So this is something you should be able to do at night if you wanted to. So some of the in-field sensors that are available include Optrix by Ag Leader, Crop Spec, of course Green Seeker, the one we're used to with Trimble, and then Crop Circle from Holland Scientific. The problem with these is, in terms of the good and bad of sensors, is they have to be calibrated. Just like a computer, they don't know what you need to know. You have to tell them. So yes, we can use these sensors for detecting in-season nitrogen status in a field, but it doesn't know the difference in the values. So you actually have to go out and put a high nitrogen strip across that field. And the recommendation for some of these fields is a strip that's 300 feet long of more nitrogen than you think the crop needs, so that the sensor can tell the difference between good and bad in the field, and you can make a recommendation for how much nitrogen to add. So yes, we can tell how much nitrogen a field might need, but we have to do extra calculations. So it's not necessarily something that's just plug and play. You don't just stick it in there and run across the field. You have to do a little more work. So in all of these cases, you have to have variability in the field. If you don't have a lot of field variability, then it's not going to be very useful to do something like this. So the Virginia approach, and they have a publication about this for wheat, you can see all the different types of information that they need. They include when you planted, how much nitrogen you put in the fall, possibly growing degree days, a lot of information that you have to enter in the field. You have to drive across a low area and a high area, and then it does a calculation, and then you drive across the field, and as it reads NDVI through the Green Seeker, it applies the nitrogen. So if you're willing to do all that extra work, you can possibly adjust the nitrogen rates in the field. But is there return on investment or not? I'm not sure. This is not research that I've done. So the nice thing about if you use a drone versus a satellite becomes that spatial resolution and temporal, because you're in charge of how often you fly. With the spatial resolution, most of the drones, of course, we're not allowed to fly above 400 feet. I'm sure some people do. I don't. But most of the images that I get, each pixel on there is probably just a few inches. The lower you fly, I get things down to 1 centimeter. So you can get really high spatial resolution. You can get really high resolution out of a drone if you actually need it. So for us in research plots, you can see a satellite image is not going to capture a research plot like it would a field in the Midwest. What I've seen around Delaware is the larger your fields are, the satellite imagery is fine. But if you're talking about a smaller field, you might not pick up the difference because this road here, whoops, I always forget which one on here is the light. I'm not going to press it, I'll turn it off again. That road that goes around that field will be calculated by the satellite as lower plant vegetation, and you'll get this kind of grading across that field. It'll look like it's low at the edge when it's just the road being calculated in, based on that resolution of 30 meters, which is about 100 feet, so that's what Landsat would be. You can pay for something that's 1.5 meters, about 5 feet, but it costs more money. So is that something that you want? So the drones can get around that. And the other nice thing about drones is we can put these multispectral cameras on there, just like satellites have, and we can calculate NDVI from it. And that way, you can fly it when you want, over the fields that you want, and you can get a lot higher resolution to possibly find some of these field differences. So right now, what I tell people about NDVI and drones is they're great for me in research. I wouldn't recommend them for farmers. I wouldn't recommend them for crop consultants yet until we've gotten the cost down. But for research plots, that high-throughput phenotyping, I'm starting to see some results from that. We're seeing data that I can fly once and then come back in September at the end of the season when I have time and calculate the data, and we have another data point to add in there to see what happened when. That's the nice thing about a drone over the season. Instead of waiting just for yield, I have measurements sometimes week to week or month to month that show us when things went wrong. And that will let us know whether our treatments went bad or whether it was irrigation or a drought or insect damage or deer damage. We've been able to spot a lot of that. All right. The problem with the NDVI out of these drones is it's got the same thing. You're going to need a reference strip. All it knows is there's a difference. It doesn't know why there's a difference. So you still have to put a reference strip out there. There's a lot of data management. There's a lot of imagery. I have a drive that I had for 2 years that has 1.8 terabytes of information on it at this point. So there's a lot of data, there's software, there's time, there's investment, there's knowledge. So I don't think it's going to be an individual. It will take group knowledge to do some work like this with drones. But the nice thing about it versus GreenSeeker is this was a project we did with a farmer where we flew the field, we created an NDVI map, and unlike the GreenSeeker that just looks at low and high, some of these low spots were dead. There was no reason. They were saturated, low spots in the field. There was no wheat. There was no reason to apply nitrogen there. The GreenSeeker might see that as low and say, I need to kick more nitrogen out to up the wheat. Where in this case, we could actually tell it before it went out there, don't apply anything, based on flying the field and our own knowledge of the field. So that's the nice thing about a drone. Instead of doing it on the fly as you go across the field, you create a map, you make decisions about here's what my zones are going to be. The same problem James has with EC maps and creating, we have to classify these things. We have to decide what is what. How are you going to describe some of these things? So here's an original field and a classification. These are human decisions. The same thing when you hear words like machine learning. Machine learning still takes people. We have to tell the computer, this is what this is. And if you're biased or you don't know what you're talking about, you can end up making a bad model. So what kind of algorithms are we going to use? How many do we need, state to state? If there's different reflectances in soil values, that's going to mess with a lot of this information. So when you hear that we're going to do all this type of work with drones, we are, but it's going to be down the road. It's not immediate, and it's not right now. And do you really need a multispectral camera? Maybe not. Same field with your regular DJI drone that costs maybe $1,000 versus something that would cost closer to $10,000 to $12,000. The NDVI is typically, imagery-wise, more accurate, but this VRI index, which just looks at your cell phone camera, could come up with that index. You can see differences in the field with it. So if you're scouting, it might be perfectly fine. I still have to analyze the numbers to see if it's comparable or not across some of our treatments. But do you need a more expensive camera? I don't think so. And there's also something else that you can do with drones. It's called structure from motion. So the old stereoscopy, where we would take two images and overlap them and draw the elevation lines. You can do the same thing with drone imagery because this is actually a stitched image on the left of maybe 100 different drone photos, all stitched together. So they're all overlapping, and this is done with drone deploy software, but you can do it with different software. This is actually, you can see the heights of the trees. It is calculated from those multiple images. So you don't need a LiDAR sensor to measure plant height. So some of the research that's being done at some of the universities, they're doing phenotyping in terms of how high are our plants, and they subtract it from that digital elevation model that they have, which might not be accurate. James and I are talking about using some of the RTK tractor data that he has to do this. But it's possible that we can measure plant height, so maybe we can do biomass of cover crops and how much nitrogen we get out of it. Because NDVI is just going to tell you the plant coverage, but if we can have height, we might have how high is that. Do you have a low growth that's covering the ground? Do you have a high growth that might have more nitrogen in it? I'll have a few more slides. So the hyperspectral sensor is another one that people can put on drones. Never buy one of these. I'm sure you won't, because as far as I know, they all cost about $25,000. They might be great for research, though, because a hyperspectral sensor looks at a whole lot of wavelengths on a very small scale. And with this sensor, they might be able, they've already shown that they can separate out different minerals or different plant types. So if we're going to do weed ID, this might be a way to do it outside of is something growing in a row that we don't want to see. And then there are also thermal cameras. Thermal cameras are cheaper. Well, that one up there is not. But the FLIR camera that you can get for $100, which you could buy and take pictures of, is there heat coming out of my windows in my house? You can attach those to drones, and some of them have georeference pictures. But the kind of work that they're doing with thermal cameras, particularly for some of the work James does with irrigation, you can detect plant stress because evapotranspiration is going to be a temperature difference. Some other work that universities are doing that are interesting is if you spray a weed with an herbicide and it dies, it should have a different thermal signature. If it is herbicide resistant, it should still be there. So thermal cameras can help with that research. It's also being used in animal agriculture to detect animals out in the field. So thermal cameras are a little cheaper. You can use them by hand. You can use them by drone. These might be something that we can use a little more often in our work versus some of the multispectral type work. So the good and the bad of all these sensors is never buy just into the sales pitch, because I can tell you that the University of Delaware and the University of Maryland have both spent money on stuff that doesn't work as advertised, and we do that for all of you guys so you don't spend the money. Weigh the options. Know what you actually want or need. Do you actually need this sensor? Is there going to be a return on investment? Sometimes we don't know yet. With the drone work, I'm trying to figure that out, so don't jump in and buy $20,000 drones. Not all technologies provide new or unique data, as James talked about. Some of those moisture sensors, the technology behind them hasn't changed, even if they advertise that it has. We don't know if there's a return on investment. A lot of these technologies need a lot of background research about, yes, they might do what they say, but is there any value in the time or the cost of actually implementing that? So I think, for me, the basic agronomics still dominate, but those sensors might help take measurements. I still lean towards a lot of this helps researchers more than it does everyone else at this point. So are there any other questions?
Do you see any value in satellite imagery?
Yes, I see value in satellite imagery if you look at it. So I've had a farmer call me before that said, my yields weren't good. Here's my satellite imagery from August. What happened? I'm like, you got to walk out in the field. The satellite imagery that you get that might show that there's a bad spot through, if they're doing NDVI or some kind of plant health calculation, just tells you it's bad. Just like with the drones, you have to walk out there and find out why. So if you're getting it, and your field's large enough, and you act on it, it's absolutely valuable. For me, what I like about satellite imagery versus yield is the same thing with a drone, is you have a seasonal history. Instead of not knowing what happened and saying, why was my yield bad in this spot and taking a guess, you actually have some information. Some of our drone imagery actually showed some of our plots with cover crops were greener in August than the ones next to them. And that helped us when we got yields out to know that there was an effect through the season. We don't know why, but we know because that imagery gives us an idea of what to look at next year, things like that.
My weekly service was providing managed once a month. I was wondering, has it gotten better?
I think some people are getting more imagery, but I also know that people had issues. If there's cloud cover, now clouds mess with drones too. So if they tell you, the clouds mess with drones, but if there's cloud cover, there's nothing they can send you. And there's a website called OneSoil. It's at a country called Belarus, and they give you all the imagery for free because in Europe, the Sentinel satellites, that data is free to them. So you can get similar imagery for free from the OneSoil website right now, but you have to go to it and sign up.
And we've been this year I took the satellite imagery. We've been flying drones too on the same field. The satellite imagery hasn't been getting a lot better because we've been seeing a lot of close comparisons. It's running, and I'm comparing the climate to the drones.
Yeah.
So,
I've definitely seen it. It's like the larger the field is, when you're talking field, for us it doesn't work.
now you brought up the root thing because we had one piece where it showed a lot of yellow along a road. And of course, we flew with the drone, and we're still kind of showing up too. Of course, and you can see it eyeball from the field, but when the yield map come up, we really didn't see.
Right.
Really didn't see it in the yield map.
And that's another problem with this technology that I see. The way it's being advertised to the public, it's like, this helps with ag. And then people that know nothing about ag, like you guys, go out and buy a drone and want to start a drone company. I'm like, if you don't know agronomics, then this is Greek to you. So everyone in this room, the information is helpful because you are here, you're studying, you understand the information. But the interpretation of these images is very important. Okay. Yes.
Considering the investment required, do you think it would be valuable for farmers themselves to invest in these technologies, or perhaps rely on something like Climate or other companies that can provide the service to do it for them?
My recommendation on drones is the ones that cost $700 to $1,000 are absolutely worth it for quick scouting. I think that for me, they have shown me very quickly in our research plots whether something was a treatment or a soil difference. You can get across a large field fast with that and see where there's damage. Maybe walk out there and maybe just write it down. So for that, yes.
When it comes to stuff like smart firmer, yeah, probably, depending on what you're trying to accomplish. So what your sensors, in some cases, yes. Varus, probably not. It's cheaper to hire it done. There are services out there that are providing that for you. So it all depends on which specific thing you're talking, what you're trying to accomplish. One of the big things is, are we just collecting data for the sake of collecting data, which we tend to do in the university level quite a bit, and then I don't know what to do with it. But there are people that have yield data for 20 years that have never really looked at that for any other purpose other than just having it. So,
I think the consulting companies, if they want to invest in buying drones and multispectral cameras and creating NDVI maps to help delineate zones for farmers, that would be fine. But I'd never tell a farmer to buy multispectral cameras.